Hello viewers, today we shall discuss Bolzano Weierstrass theorem, and today in one complete lecture we discuss the theorem that is Bolzano Weierstrass theorem, that is for sets. Utmost care has been taken to make the presentation easy and fundamentally strong. The theorem states that every infinite bounded subset of real numbers has a limit point. I repeat, every infinite bounded subset of real numbers has a limit point. We see that there are two conditions on the subset of the theorem. The conditions are: the set must be an infinite set, it must be bounded. The result then guarantee that such a subset which is infinite as well as bounded must has a limit point. So every infinite bounded subset of real numbers has a limit point. Before going to the proof of the theorem, and to make the picture clear, we first discuss examples where a set which fulfill both the conditions has a limit point. Then we shall also discuss examples where if there is a failure for any one of the two conditions, then the set may or may not have a limit point. So it is one-way theorem. Converse of the theorem need not be true. So first take an example. Let S is equal to be the set 1, 1 by 2, 1 by 3, 1 by n and so on. Of course the set is an infinite set. Also 0 is less than 1 by n is less than or equal to 1 for every natural number n. The set is bounded as well. So this set S is infinite and bounded set. The bounds of the set are 0 and the upper bound is 1. We know that for this set 0 is a limit point. So this is an example which justifies the theorem that set is infinite as well as it is bounded, so it has a limit point. Now we take another example. Let S is equal to the set of natural numbers 1, 2, 3 up to n and so on. S is the set of natural numbers which is infinite and unbounded. Okay, the set has no limit point. We know it. The derived set of the set of natural numbers is empty. Okay, thus the drop of any of the two conditions may lead to non-existence of limit point. Here the condition of boundedness is dropped, so it does not have a limit point. Further, if it is a finite set, suppose S is a finite set, then it does not have a limit point. So if any one of the two conditions drops, then the set need not have a limit point. Thus the drop of any of the two conditions may lead to non-existence of a limit point. Now we take an example which shows that the theorem is one way. The theorem is one way and converse of the theorem need not be true. For justification, we discuss an example. Let S is equal to 1, then 2, 1 by 2, 3, 1 by 3, n, 1 by n and so on. This set S is a union of two sets, S1 which consists of all the natural numbers and S2 which consists of all the fractions 1, 1 by 2, 1 by 3, 1 by n. The set S1 and S2 both are finite, so the set S is an infinite set. Okay. One of the subset S1 is unbounded. So S is also unbounded, because if a subset is unbounded, then set itself is unbounded. Here one of the two conditions, the condition of bounded set, is dropped. Okay. So we can clearly see that this set S, which is infinite but unbounded. Now 0 is the limit point of the set S2. We have just shown in the previous example that 0 is the limit point of the set of the numbers 1, 1 by 2, 1 by 3. S2 means 1 by 2, 1 by 3, 1 by n, and therefore is a limit point of the set S. So it is an example where S is an infinite though unbounded, but still has a limit point. Before proceeding to the proof of the theorem, we make clear the meaning of at the most, which we shall use in the proof of the theorem. So let S is equal to X such that X exceeds a finite number of primes. X is a natural number. The set S is the set of natural numbers for which the natural numbers exceeds a finite number of primes. As per condition laid in the set, a number can be a member of the set if it is a natural number and exceeds some prime numbers finite in counting. As per the conditions laid on the set, that must be a natural number and must exceeds a finite number of primes. Observe that one is a natural number but does not exceed any prime number. The natural number 1 cannot be included in the set. Similarly, the natural number 2 not exceeding any prime number cannot be a member in the set S of the set. All other natural numbers are included in the set. You see 3 exceeds a prime number, that is 2, 1 in counting. 4 exceeds 2 prime numbers, 2 and 3. 5 exceeds 2 prime numbers, 2 and 3. So all these are numbers, natural numbers which includes in the set S. Now let us make a little modification to the set S. Okay, that S is equal to X such that X exceeds at the most a finite number of primes and X is a natural number. Now there is a little modification where in the set S, X exceeds a finite number of primes and X is a natural number. Here X exceeds at the most a finite number of primes and X is a natural number. The condition now have two options, that a natural number which exceeds a finite number of prime is in the set, and a natural number which does not exceed any prime is also in the set, because here is the word at the most. Now we move to the theorem popularly known as Bolzano Weierstrass theorem. Here we go back to the set S. S is the set X exceeds at the most a finite number of primes, and X is a natural number. So this set becomes the set of all the natural numbers. This set S now, one is included in the set. One, 2, 3 and all the natural numbers are included in this set S now. We move to the theorem. Now we move to the theorem popularly known as Bolzano Weierstrass theorem. We put a very simple and compact proof of this theorem. The theorem states that every infinite bounded subset of real numbers has a limit point. Let S be an infinite bounded subset of real numbers, and suppose that small m and capital M are its greatest lower bound and least upper bounds respectively. Okay, let me construct another set. Let A be the set having the property that a real number is a member of in A if and only if it exceeds at the most a finite number of members of S. That means X is equal to X, such that X is a real number and it exceeds at the most a finite number of elements in S. Clearly set A is non-empty, set as M belongs to A. Now M is the greatest lower bound, does not x at any point of A, so that is included in A. So small m belongs to A. Also A is bounded above as no real number greater than M can belong to A. Therefore, by completeness axiom of real numbers, set A has least upper bound. And let x0 be the least upper bound of the set A. We shall prove that this x0, which is least upper bound of the set, is a limit point of the set S. That is our task, to prove that x0 is a limit point of the set S. So let epsilon greater than 0 be a number, as x0 is the least upper bound of the set S. Therefore, there exists a real number x of A such that x is greater than x0 minus epsilon. Let us say this as 1. It is an important thing, so we give it a number 1. As x belongs to A, it exceeds only a finite number of elements of S. Now, x0 minus epsilon is being smaller than x, can exceed only a finite number of elements of S. Also, x0 is supremum of the set, therefore x0 plus epsilon cannot belong to the set, to A, and consequently exceeds infinite number of elements of S. We give this definition as the number 2, 3 and the previous one, that is 2. From these two conditions, we conclude that x0 minus x0 plus epsilon, x0 plus epsilon, x0 plus epsilon is a neighborhood of x0 and contains infinite number of elements of S. This will be true for each epsilon greater than 0. Therefore, every neighborhood of x0 contains an infinite number of elements of S. Therefore, x0 is a limit point of the set. And this is the proof of the theorem. Thank you.